This is Group 7's project presentation on COVID death rates in cities across the U.S., presented by Matthew, Jake, Julianne, Alex, and Pratim. The world has been dealing with the COVID-19 pandemic since March 2020, when many countries around the world imposed national lockdowns to control the spread. Fast forward to November, and the U.S. is now again dealing with rising cases, hospitalizations, and deaths as we enter into the winter season. The U.S. alone has seen 12.7 million cases and more than 260,000 dead from COVID-19 as of November 25, 2020. However, the effect has not been homogeneous across all states and cities. Our goal was to investigate what characteristics of a city and its population impact the death rate of COVID-19. I should note this is an exploratory observational study only, and there are many other factors that were not included in this dataset that can affect death rate. A recent article published in July 2020 in Science Direct by Wang et al. Also had the similar goal of predicting death rate of COVID-19 in certain Chinese cities and provinces. However, they projected death rates using an algorithm that took into account average days of hospitalization of the infected that could change and reflect numbers real time. From our dataset, we were given the death rate of 47 U.S. cities, along with explanatory variables such as city area, median age, median household income, number of hospitals in the city, city population, percentage of the population in poverty, and the percentage of the population that were without health insurance. Our goal was to determine which of these predictor variables were actually significant, or in other words, which of these predictor variables had a linear impact on the death rate. Much has been said about COVID primarily affecting the elderly, so specifically we wanted to see if the median age of a city had a significant impact on death rate. Since this is also a fast-spreading virus, we figured how well a city was able to handle large amounts of patients would also factor in, as well as the ability for said patients to afford treatment, which led to us testing if the number of people or population per hospital and the poverty rate of a city would have an impact on death rate. We conducted a t-test for each predictor with the null hypothesis that each predictor did not have a significant impact on death rate.
Now that we have an idea of the questions that we're going to be asking along with the hypothesis and understanding the data more, we need to look at the variables and understand how these are going to impact our model. Looking at the different variables from the dataset that we were given, there are a total of 9 different variables with a sample size of 47. The response variable is going to be the death rate, which is the percentage of deaths that occur from COVID within a city. The explanatory variables are going to be city area, median age, average median household income, number of hospitals, city population, percentage in poverty, which will be the average rate of poverty in a city, and then percentage without health insurance, which will be the percentage of people without the insurance in the area. Out of the data set that we were given, all the information from the previous slide was from sheet 2. We did not exclude any numbers or variables from that sheet. On top of this, we also decided to create a new variable, which will be population per hospitals. This will end up being the city's population or people divided by the number of hospitals in that city. This will also end up being another explanatory variable, which will help us define the model for the death rate.
Now we'll do a preliminary analysis of the scatter plots and see the trends between the death rate and the predictor variables. With the death rate versus without health insurance, we see that the relationship is somewhat flat, and it also appears to be kind of linear but flat. and there are 2 outliers. So for the death rate versus population, we see that the relationship doesn't really appear linear. It looks like a bunch of scattered points towards like 0, from 0 to 2 to the 10 to the power 6 for population, and 0 to 4 for death rate. So yeah, for death rate versus population, we may have to do like some transformation. The same thing is true for death rate versus person per hospital. And for the death rate versus number of hospitals, we see that the relationship appears to be somewhat strong, not too strong, but it appears to be kind of linear, but also kind of flat, and there are also 2 outliers. For the death rate versus poverty rate, we see that the relation is quite linear, but there are also 2 outliers. So that one, we would likely not change that because of the pretty strong relationship. With the death rate versus area, the relationship appears to be very slightly exponential, but it also kind of appears linear, but it doesn't appear to be a very strong linear relationship. So we might have to do a transformation, and there are also 2 outliers with the death rate versus area, so we might have to like remove those. The same thing is true for the death rate versus average household income. The scatter plot also remains kind of flat and somewhat linear with outliers. And the same thing is true for death rate versus the median age. That you have a linear plot, you have a linear relationship for the most part, but it's kind of flat, and you have 2 outliers. So given the basic linear model of the death rate versus all the predictors, the residual plots are shown. So when we see that we have the residuals versus population, we see that there isn't really any constant variance. Like, everything is kind of concentrated towards where population is like between 0 and 2 into 10 to the power 6. In that region, the variance appears kind of constant, but after that, with like that outlier to the right, it appears high. And for the residuals versus like the number of hospitals, we see that the residuals appear not to have like a constant variance with like the number of hospital intervals, so that one would have to do a transformation. For residuals versus median age, the variance appears somewhat constant, but there are also instances where you don't have constant variance. The same thing is true for residuals versus area. It's basically like some of it might appear constant with the variance, but also you have inconsistency with the residuals. With the residuals versus person per hospital, we see that there is like one big outlier towards when the persons per hospital is like really, really big, or else beyond that we see more or less somewhat constant variance as we go to the left in persons per hospital, but as we go to the right, the variances become smaller. With the residuals versus poverty rate, we see that the variance is fairly consistent with poverty rate between 10 and 0 and 20, but after that the variance appears very non-consistent. For residuals versus without health insurance, we see that the residual variance appears more or less constant, but then there are also cases where it's also kind of non-constant. With the residuals versus average household income, we see that the residuals appear more or less constant from past average household income of 4 into 10 to the power 4. But before that, the residuals appear kind of non-consistent. So we probably have to do like some transformations on all of those things.
Now that we have an understanding of the dataset characteristics, more specifically, the relationship of each individual predictor to the response, we can begin to create our model. The first model that we'll create is the first order model. This means that we'll linearly place each predictor into a model with the response. Based on the summary call on the model, we can see that there are 3 terms that are significant at a level of 0.10, poverty rate, without health insurance, and person per hospital. Looking at the rest of the summary function call on the first order model, we can see how appropriate the model was for the dataset. The adjusted R-squared value is moderately strong at about 0.6241. The F statistic generated from the GLT test is significant at a very small p-value. This means that the dataset and the predictors in this dataset do a good job of predicting the response. Next, we must ensure that our model is appropriate for the dataset. We do this by checking assumptions. The first assumption that we will check is the constant variance of error terms. This is done by running the Brown-Forsyth test. When we ran the Brown-Forsyth test, it produced a p-value of about 0.095, which is not significant at a level of 0.05. This means that there were not signs of non-constant variance. That means our assumption checks out. The residuals versus median age plot shows a prime example of constant variance. This is what we're looking for. While the residuals versus person per hospital plot shows non-constant variance and something that we should keep an eye out for. The next assumption that we will check is for the normality of error terms. This is done using the Shapiro-Wilks normality test. When we ran this, we generated a very small p-value that was significant at a level of 0.05. This means that there are signs of non-normality among the error terms. We can see this also in the normal QQ plot. The points deviate from a line and are dragged up on the far right side and down on the far left side. The histogram of error terms also shows a skew to the right. This violation of the normality of error terms is something that we'll keep in mind down the road when we're adjusting our model. The final assumption that we will check for our first order model is the assumption of independence. This is difficult to check in multiple linear regression, so we decided to check for multicollinearity to make sure that the predictors are independent of each other. A VIF of larger than 10 signals that there is some sort of multicollinearity that exists. We wrote a function in R that checks the VIF for every combination of predictors when the other explanatory variables are used to model these predictors. The VIF is only larger than 10 for population and person per hospital, and this is because the population variable was used to create the person per hospital variable. We expected these results. Therefore, there's nothing to be worried about, and we believe that our assumption for independence has been met. Now that we have checked the assumptions for our first order model, it's time to run some diagnostics. The first diagnostics that we ran involved checking for outliers. When we check for Y outliers, we used the studentized deleted residuals method. This method identified one case that was an outlier with respect to Y. To check for outliers with respect to X, use the hat matrix leverage values. This identified 3 cases that were outlying with respect to X. We then ran Cook's distance, and it found that these 4 points were the most influential points on the dataset. We will take measures later using robust regression to account for these influential data points. In addition to checking for outliers, we also examine the added variable plots. These plots give a really good idea of the marginal importance of a predictor. The more magnitude of the slope of an added variable plot, the more marginal importance it has. We can see that poverty rate, without health insurance, and person per hospital show the most marginal importance of all predictors. This is consistent with the findings that we had when looking at the summary call on the first order model. Before any remedial measures will be made on our model, we decided to run automatic model selection. We used the best subset algorithm to do this. One of the goals of our model was to maintain model interpretability. So, when there was a tie between the model containing 3 predictors and an intercept and 4 predictors and an intercept, we decided to go with the model containing 3 predictors. However, one of our hypotheses relied on median age, and it was not selected in this best subset algorithm. Therefore, we added median age back to the model. So, the model that we would be pursuing had 4 predictors and 1 intercept: median age, poverty rate, without health insurance, and person per hospital. One of the problems that we were running into was the influential cases and the effect that they had on our model. So, to deal with this, we ran robust regression on our subset of 4 predictors. As you can see from the k-fold cross-validation below the summary call on the robust regression model, the root mean squared error decreased quite a bit from what it was in the first order model. The r-squared, which was adjusted, also increased. This is a good sign. This means that we eliminated some of the influence of those outlying cases. Just like before, we have to make sure that we check assumptions on any model that we are creating. When checking assumptions on the robust regression model, we can see that the p-value for the Brown-Forsyth test increased greatly. This is a good sign. This means that there is more evidence of constant variance of error terms. When looking at the check for normality, we can see that the points follow a much more linear pattern, and there's only one point on the far right side that really deviates from this pattern. Finally, when checking for independence, we see that there are no VIF values that are larger than 10. Based on these assumptions, we can be sure that this robust regression model is a good way to represent our data and predict our response, death rate. This leaves us with our final model. As we can see, there are 4 predictors and 1 intercept term here. Poverty rate has the most influence on death rate. In fact, a 1% increase in poverty rate actually increases the death rate by 0.15%. The one surprising result from this is that without health insurance, so those who do not have health insurance, when that percentage increases by 1%, the death rate actually decreases by about 1.4%. This is not a fluke. We actually saw, when plotting without health insurance versus death rate, there was a strong negative linear relationship. Now that we have developed our model, we're going to test some hypotheses that we have about the predictors in that model.
We had 3 hypotheses that we wanted to test. The first one is whether the median age of a city has an effect on the death rate. We used a two-tailed t-test for this, where the test statistic was 2.32 and the t-value is negative 1.098. As a result, we did not reject H0, and the median age was determined to not be significant. The second is whether the amount of people per hospital has an effect on the death rate. We also used a two-tailed t-test for this, where the test statistic was 2.32 and the t-value was 6.765. As a result, we rejected H0 and we determined that the coefficient estimate for the number of people per hospital was a significant factor. The third hypothesis that we tested is whether the poverty rate has an effect on the death rate. We again used a two-tailed t-test to test this hypothesis, where the test statistic was 2.32 and the t-value was 5.67. As a result, we rejected H0 and we determined that the coefficient estimate for the poverty rate was a significant factor. There were a few issues that we ran into while working on the project. First, the poverty rate and health insurance data was in a percentage, but death rate was a decimal, so we had to convert death rate to a percentage as well. Second, we had a few outliers and influential cases, so we decided to use robust regression to minimize the influence of these cases, rather than just remove them outright. We think that all of the data points for this project are important and accurate, even though they might be outlying. Finally, our goal was to make a simple enough model that is readable, rather than a more complex one. So we had to try and make a good model without making it overly complex. The three factors that we determined contribute significantly to the COVID death rate are the poverty rate, the percentage of people without health insurance, and the amount of people per hospital. There were 5 predictors out of the 8 that we tested that we determined to not be significant, either through model selection or through hypothesis testing. These 5 predictors were city area, average household income, number of hospitals, population, and median age. Overall, COVID is a complex disease that we are still learning about each and every day. As more data becomes available in the future, our model that we have will certainly change. Our model was based on early data from the first wave of COVID. There's a much larger wave of COVID currently happening in the US, so as more data comes in, the model will change. And we as a society must continue to use data that has been gathered previously and is still to be gathered about COVID in order to slow this dangerous disease.